But in order to understand melody, the backbone of the Preston guitar method, we first have to learn how to speak her language. Can you imagine a language that uses 26 letters, and any combination of those 26 letters forms words, sentences, phrases, paragraphs, and it's a very effective means of communication. That's our English language, A through Z. Now, can you imagine a language that only uses 7 letters, and any combination of those 7 letters form a very effective means of communication? So effective, in fact, it's called the universal language. That's the language of music. So the question is, why is music considered the universal language? Well, let me ask you this. Do you speak Russian, Vietnamese, Chinese? Yet, you can communicate with people of all types through music. And you can go a step further than that. Right now, as I'm recording this, we are in the middle of a pandemic. We are also in the middle of an election where one side is polarized to think this way, the other side is polarized to think that way. And you simply cannot get the two to meet in the middle. I just don't want to hear this record. If you've ever spoken to someone who's depressed, and you use good words and you organize your thoughts and you try to give them comfort, but it seems like it just doesn't work. It seems like you just are not getting, or that you just can't get through to them. Yet, with music, you can. You see, I'm going to play a song for you. Greensleeves. And let's imagine for a moment that you and I speak a totally different language. Let's say that I speak English and you speak Chinese. Can you tell me how I'm feeling based on the way that I play this song? Now, I'm going to play the exact same song again. Think about that. The first time I played it, I sounded sad or somber. The second time I played it, I sounded happier. With music, it's not only possible to communicate your emotions to other people, but you can affect their emotions so that they begin feeling the way that you feel. If I want someone to slow down and feel melancholy, I'll play in a melancholy way. It doesn't matter what language they speak. If I'd like someone to be up and having a good time, I'll do that too. I really don't like the way I did that up. I don't know if I can do that. I can't believe I said up.
Take 2. Play happy to make your audience happy. Action.
If I'd like to influence someone to feel better, maybe a little happier, that's the way that I'll approach music, because it's the universal language. Only 7 letters. That's right. No K's, no T's, no P's, no Q's or R's to worry about. Only A, B, C, D, E, F, G. And when you get to G, you start over again. A, B, C, D, E, F, G, A, B, C, D, E, F, G, on and on into infinity. Now, what do I mean by that? On and on into infinity. Well, I think it's time to take you to the woodshed. Hello, welcome to the woodshed. This is the place where we obtain the tools and develop the skills necessary to assist us on our guitar playing journey. Today we're going to be talking about frequencies and how frequently they relate to infinity. Now, the last time we got together, we talked about how an acoustic guitar produces sound. Let's take a look at how this acoustic guitar produces sound. When I pluck the strings, we hear the sound. But what's actually happening can be explained through math. If I were to pluck a string, you can see that string vibrate back and forth. Let's zero in and look at that string vibrating a little bit deeper. And it's quite fortuitous that I actually broke the very string I used in the last example. Let's talk about that string. Let me just snip that off here real quick. There we go. Okay, this string is a cylinder, and if I put it under lateral tension and stretch it, it wants to remain straight. Now, if I do a pluck, that's called the fundamental. That's the thing that gets it vibrating. You can see the string vibrating. Oh, I'm sorry, congruous B-roll. Okay, like I said, when you stretch the string, and especially if you put it under lateral tension, it wants to remain straight. When I pluck it, it vibrates. Okay, now let's blow this up and make it a bigger picture. This dowel rod represents that string. And if I were to put lateral tension on it and stretch it from end to end, it definitely will want to stay straight. Let's take a look at this little contraption. I've got a board here with a black line drawn on it. We're going to refer to that as the baseline. I'm going to call this the butterator. Let's get into it. Okay, I've got the dowel rod inserted into the butterator, and you can see right here, here's the baseline. Now, this string wants to be straight, especially if we put lateral tension on each end. And when I pluck it, watch how quickly it wants to go back to straight. That happens rather quickly. If we kind of blow that up and take a closer look, what's happening is after the fundamental, the string wants to go straight, but it overshoots the baseline, tries to correct itself, and goes back and forth until it loses energy and decays and doesn't vibrate any longer. The number of times that it overshoots the baseline on the top, on the bottom, and then corrects itself is called a frequency or a cycle, and it's measured per second. How frequently does that occur per second? We also refer to that as a hertz, H-E-R-T-Z, or abbreviated Hz. Now, what's with the funny name? See, we owe all of this to a man named Heinrich Hertz. In the 1800s, people had a theory about magnetic waves. But in 1886, he was the one that defined how to measure the cycles of these magnetic waves. Now, his peers, in order to honor him, started using his label, his last name, to say, oh, that string is vibrating 14,000 cycles per second or 14,000 hertz. And why not? I mean, if I had discovered it, they'd be called buds. Hey, that sucker's vibrating 4,792 buds per second. Later in his career, he started quite a lucrative business in the car rental industry. Now, with this newfound knowledge, let me help you draw a few mental pictures. Remember, a string is a cylinder. And especially when it's under tension, it wants to remain straight. Once it's plucked and pulled out of straight, it starts a repeating cycle. First, in an attempt to return to straight, it overshoots the baseline. Then, in an attempt to correct itself, it undershoots the baseline. This is one cycle of a string's travel. The number of times that it does this in 1 second is called the frequency or the hertz. The word cycle derives its name from the Greek word kyklios, which means circle. Now, right now, that's just a bunch of yellow snow. If technical terms and words of origin are important to you, then by all means, do some research. However, for now, what's important is that we grasp the general principle that the word cycle comes from the word circle. If that's the case, then why do we not use a circle as the device to measure vibration patterns? Well, the answer is easy. It is very difficult to visualize a spinning circle, continuously cycling around and around until its job is done. Now, the automotive industry has solved this very problem out of necessity because, well, an engine spins or rotates. They measure the number of times an engine completes one cycle with RPMs, or how many revolutions it performs in a 1 minute time frame. Revolutions per minute. To accomplish this, they have ingeniously created a device called a tachometer, which tells them either digitally or analog the number of times that the engine is cycling per minute. We can very easily see how the cycle of a string, and therefore a sound wave, owes its inheritance to the circle. Take a circle, bisect it, then spin it on its axis, and voila! You now have a very understandable visual representation of one cycle of a sound wave, or a sine wave. A sine is very simply a curved pattern that repeats. Here we have one cycle of a sine or a sound wave in a 1 second time period, which is referred to as 1 hertz. And here we have 2 cycles of a sound wave in a 1 second time period, which would be referred to as 2 hertz. We can also describe the sounds of these strings vibrating, causing sine or sound waves by their pitch. And pitch can best be described this way. Take a rubber band, stretch it between your thumbs and fingers, and pluck it. You can see the rubber band vibrating, but you can also hear it. Now, stretch the rubber band tighter and pluck it again, and 2 things will happen.